Right now, in another universe, you made a different choice. You took a different job, married a different person. Maybe you never existed at all. This isn't science fiction. This is what the equations of quantum mechanics actually predict, and the physicists who discovered it wish they hadn't. It started with a simple question: what is light, a wave or a particle? In 1801, Thomas Young fired light through two tiny slits and watched what happened on the wall behind. The result was impossible. Instead of two bright lines, he saw an interference pattern, like ripples in water overlapping. Light was behaving like a wave. Fine. Weird, but fine. Then, a century later, physicists tried the same experiment with single electrons, fired one at a time, one by one. No two slits, just one electron, one detector. The interference pattern still appeared. How does a single electron interfere with itself? It would have to travel through both slits simultaneously, be in two places at once. That's not a glitch. That's not a measurement error. That is quantum mechanics telling you something deeply uncomfortable about reality. In the 1920s, Niels Bohr and Werner Heisenberg proposed an explanation, the Copenhagen interpretation. Before you observe a particle, it doesn't have a definite position. It exists as a wave function, a mathematical cloud of all possible states simultaneously. The moment you look at it, measure it, the wave function collapses. It picks one reality, the other possibilities vanish. This became the official answer, the one taught in every textbook. But one young physicist at Princeton thought it was a cheat. His name was Hugh Everett III, and his question was simple, brutal, and career-ending. Where do the other possibilities go? It was 1954. Everett was 24 years old. He sat with the equations. He followed the math, all the way to the end, without flinching. And the math said this: the wave function never collapses. Every possible outcome of every quantum event actually happens. Not in sequence, not randomly, all of them, simultaneously, in separate branching realities. When the electron passed through the double slit, it didn't choose one. The universe split. In one branch, it went left. In another, it went right. You, right now, are one branch of an unimaginably vast tree of realities that has been splitting since the Big Bang. Everett called it the relative state formulation. We call it the many worlds interpretation. His thesis advisor, John Wheeler, told him to water it down. The physics community rejected it almost entirely. Everett left academia, went to work in military research, and died at 51, never knowing that decades later, his idea would become one of the most seriously debated theories in all of physics. Here's what makes the many worlds interpretation so hard to dismiss. It doesn't add anything to quantum mechanics. It doesn't require new particles, new forces, new assumptions. It just takes the Schrödinger equation, the most tested, most successful equation in the history of science, and applies it universally, to everything, without exception. No collapse, no special role for the observer, no mysterious boundary between the quantum world and the classical world. Just the math, taken seriously. The equation describes a universe that branches. So, either the equation is wrong, and it isn't, we've tested it to extraordinary precision, or the branches are real. That's not philosophy, that's logic. The universe doesn't pick one outcome, it runs all of them. Every radioactive atom that decays, or doesn't, splits the universe. Every photon that hits your eye, or misses, splits the universe. Every quantum event, at every scale, in every particle, everywhere in the cosmos, at every moment since the beginning of time. The number of parallel branches isn't a billion, it isn't a trillion, it isn't a Googleplex. It's beyond any number language can meaningfully express. And in each one, stars formed differently, planets took different orbits, evolution took different paths. Some branches have no Earth, some have no sun, some have no matter at all, and in a vanishingly small but non-zero number of them, there's a version of you reading about this exact moment, making a completely different choice about what to do next. If many worlds is true, it breaks our intuition about almost everything. Death, for instance. In some branches, you survive every near miss you've ever had. In others, you didn't make it past childhood. Decisions lose their weight. Every choice branches into all outcomes anyway. Even identity becomes strange. Which branch is the real you? The answer, according to the math, is all of them. You are not one person on one timeline. You are a pattern, repeated, diverging, spreading across an infinite probability space. That is either the most terrifying thing you've ever heard or the most liberating. Here's the frustrating truth. By definition, the other branches are inaccessible to us. Once decoherence occurs, once a quantum event interacts with the environment, the branches stop interfering with each other. They become, for all practical purposes, separate. You cannot visit the other universe. You cannot communicate with it. You cannot detect it directly, which is why critics call many worlds untestable and therefore unscientific. But there's a twist. Quantum computers might offer a clue. Quantum computers work by running calculations across superposed states simultaneously, effectively borrowing computational power from what some physicists argue are parallel branches. If quantum computers continue to outperform classical ones in the ways theory predicts, it won't prove many worlds, but it will be exactly the kind of result you'd expect if the branches were real. The universe, it seems, might be leaving fingerprints. String theory, which we explored in our last video, predicts extra dimensions. The inflationary model of the Big Bang predicts bubble universes, each with different physical laws. Quantum mechanics predicts branching realities, three completely separate corners of physics, all pointing at the same uncomfortable conclusion. What we call the universe may be a vanishingly small corner of something so vast, so strange, that we don't even have the right words for it yet. The multiverse isn't where science fiction ends, it might be where science begins. Hugh Everett followed the math, wherever it led. Most people weren't ready. Maybe now we are. The universe you're sitting in right now is real. Your choices matter in this branch. The people you love exist here. But somewhere in the vast probability space of all possible realities, every story that could ever be told is being told. Every life that could ever be lived is being lived. And this one, this exact one, is yours. This is your host, and you are watching Quanta and Cosmos. Let us know your thoughts and comments, and if you have not subscribed to the channel yet, please do for more amazing stuff we will bring in next videos.